Okay, in this video we're going to start talking about the Jordan curve theorem, or the generalized Jordan curve theorem. So the kind of introduction to what this is about, let's think about consider, suppose we've got k less than or equal to n, and I is going to be the inclusion of sk and sn. Okay. Some more detail. So sk, remember, is a set of those x in r to the k plus 1. Square norm of x is 1. And Sn we can think of, I'd like to kind of keep the, separate out the first k plus 1 coordinates and the rest. So I'm going to think of this as a pairs x, y in r to the k plus 1 cross r to the n minus k, where square norm of x plus the square norm of y is equal to 1. Okay, and this picture ix is just x0, and so let's consider the complement Sn, and we remove this included sk. So that's a set of pairs xy as above, but where y is non-zero. Okay, so here of course y is equal to 0, here y is not 0. And so we can define j from Sn minus k minus 1 to Sn removing sk by j of y is just 0y. Okay, remember, so here this is the same kind of y, so y was a vector in r to the n minus k, it's going to be a norm 1, and so that means that it's unit vectors in Rn minus k, of course that's Sn minus k minus 1 as I've written here. And then we can define r in the opposite direction. Okay, so if we've got some pair xy here in the complement of isk, so y is non-zero, so it's meaningful to normalize it like this. And so we find that r composes j is equal to the identity. And j composes r is not the identity, but we do have a homotopy. We can define h from homotopy from this space to itself by h of t x y is going to be tx comma y divided by the square root of t squared norm x squared plus norm y squared. And again, here we're working on this space here where y is non-zero, so the square norm of y is strictly positive, so this quantity here is strictly positive. It's meaningful to take the square root, and that will cause this to be a unit vector, so it will actually lie in this this space. Okay. So this gives a homotopy from j composed with r to the identity. So we see that Sn with I of sk removed is homotopy equivalent to Sn minus k minus 1. And therefore the homology of Sn less I of sk is isomorphic to the homology of Sn minus k minus 1. Okay. I should say all this kind of works, all this works on the assumption that that actually k is strictly less than n. So we should maybe say, let's just say k is strictly less than n here. k was equal to n, then this would just be the identity, and your Sn with isk removed would just be the empty set. Okay, so slightly different features there. Okay, then so let's let f from S1 to okay, so now we could think let's let f not be so here I'm thinking about f going from S1 to R3, and in a bunch of places in this discussion, we're going to remember that if you take S3 or Sn in general and you remove a point, then by stereographic projection that's homeomorphic to Rn. So throughout this section we're often going to consider Rn as being a subspace of Sn like that. So here we're thinking of S1 in R3, so that's a circle, but we're going to consider, for example, a knotted circle. Okay, so you have a trefoil knot or any other kind of knots that occur in the knots and surfaces course or anything like that. Okay, so a moment ago we were thinking about S3 with I of S1 removed. Removing the kind of standard unknotted circle, but now we're removing a knotted circle, and you get something much more complicated. However, the kind of big theorem, the surprise is that the homology of S3 less FS1 okay, so remember, homology of S3, remove I of S1, you get the sphere of dimension 3 minus 1 minus 1, which is 1. So so the homology of this, as we've said, the unknotted thing, you just get the homology of S1. And the claim is we still get the homology of S1, even though this space here is more complicated. Okay, so that's, in fact, we can state the generalized Jordan curve theorem. So this says that if X is a subspace of Sn and X is homeomorphic to Sk, so if K is strictly less than N, then the homology of Sn with X removed is isomorphic to the homology of Sn minus K minus 1. And as a kind of exceptional case, if K equals N, then X is just equal to Sn. Sn less X is empty, and well, the homology of the empty set is just 0. So that's our generalized Jordan curve theorem, and so we'll start the proof in the next video.